Welcome to the preview session. Our first speaker is Chung-Kil Hur
Yeah.
from Seoul National University.
Yeah. Okay, thank you. So we'll talk about concurrency and linearizability and background, and then the papers. So in general, for my verification, we need two things. So we have many features in CS, and then phenomena in CS, and we need to find the right models to capture those phenomena, and then for formal verification, we also need the right form of specification and then verification techniques, right? But finding formal models itself is valuable even without considering verification. And then in this talk, for concurrency, what you need is that first we have to find the right models. So there are variations of models because concurrency is a very complex phenomena. So we know some simple sequentially consistent model and relaxed model, and also even non-volatile memory model. So there are various models. And also we can validate these models by testing and then proving certain properties. And for specifications, we can give specification as pre and post conditions, and then as a verification technique, use the separation logic, for example. Or we can give a specification as abstract program, and then refinement between the concrete implementation and abstract program, and the proof technique is simulation relations. Or maybe early version is kind of a linearizability. That's a form of specification. And then to prove linearizability, there are several custom techniques, and simulation and separation logic can be also used. And so that's in general concurrency viewpoint. And then in this session, the papers make advances on this linearizability specification, and then also the proof techniques, and based on SC or relaxed and MVM, all of them are used in this session, papers in this session. Okay, and then, so I will first give the notion of linearizability first, and then we'll talk about weak memory a bit. So first assume SC models. SC model is simply multiple thread execute interleaving way. Just each thread takes one atomic steps, and the other thread may take atomic step non-deterministically. And there is a normal notion of memory. If the value is written to the memory, then the later operation should read that value, right? So that's a kind of most intuitive model. And then linearizability on that SC model is a form of specification. So consider this simple program. I will give an example and explain. So this two thread does inc. And inc is simply, there is a shared counter initialized as 0, and then inc increment by 1, and then return the incremented value, okay? So inc may give a result 1, 2, 3, 4 as a return value. And then now I will give a real behavior on the SC model, okay? And then this program may behavior in this way, and then this is timeline. So at the beginning, maybe inc 2 in the thread 2 may be invoked, so it starts to execute. And then in the middle, thread 1, thread 1's inc may be invoked and then start to execution, right? And then at this point, inc 1's the thread 2's inc may be completed and then return 2. And then still thread 1's inc keep executing, and at this point, second inc is invoked in the thread 2 and then execute, and at this point, the first inc of thread 1 returns 1, and then keep executing, and then this one returns 3, and then thread 1's second inc is invoked, and then at this point, it's completed and return 4. That's one possible execution sequence, right? And then we can say that this behavior, this particular behavior is linearizable. If we have some kind of, so for this given behavior, if we can sequentialize this method calls, for example, in this case, this inc 1 comes first, and then this inc comes second, and this inc comes third, and this inc comes fourth. So we gave a linear order on every method call, right? And then just run the same code in the sequential setting. So first inc 1 is executed completely, then you get 1. And inc 2 is executed completely, then you get 2. And inc 3 increment the shared counter and then return the value, so it's a 3, and then next 4. So you just fix linear order and then compute it. And then all the return values matches. For example, here matches, right? 1, 1, 2, 2, 3, 3, 4, 4 matches, right? Then we say that this behavior satisfies this linearized invocation sequence, right? So we can linearize this concurrent execution into sequential execution. Then we say that this behavior is linearizable. So whether every behavior is linearizable, that's one form of specification, right? So just I want to give an example which is not linearizable, okay? So this is linearizable, but assume that it's exactly the same ink and ink, but assume that ink internally is implemented in two steps. First, increment share the location, share the counter, and then read from the counter again and then return. Then what can happen is this first ink, both ink may return 2 because both ink increment share the counter, and then they read the value from, then they may read the 2, right? And then the possible behavior execution in that implementation is reading 2, 2, and 3, 4. Right, so this part is changed from 1 to 2. That's the difference. And then whether we can linearize, that's impossible because, for example, if we give this linear ordering, ink this one, this one, this one, this one, then in the linear execution, it will give 1, 2, 3, 4 because it increment and then read, increment and read, increment and read. You get 1, 2, 3, 4. There's no way to get 2, 2, 3, 4, right? So this is not linearizable. So some program is linearizable, some program is not. So that's the specification. Okay, so that's linearizability. And then, how many minutes? Huh? 3 minutes, okay. And then now I just give a notion of relaxed memory because the SC model is simple model. But to understand the relaxed memory phenomenon first, let me give you this example. So this is a simple one-time message passing. So you have two locations, shared location D and F. D is the data location, F is a flag. So when you want to send the 42 to this thread, then you first write 42 to D and set the flag to 1. And then this thread keep reading from F until it becomes non-zero. So basically reading 1, right? Then you read from D. Then you can expect that you should receive 42, right? So in the sequential SC model, you must read 42 because you read 1, and then it means it happens after this one. And before that, 42 was written to D. So you must read 42. Right? But in the reality, actually you can read here in this program, you can read 0 or 42 because compiler and hardware may optimize. So actually compiler and hardware can optimize reorder F equal 1 before D equal 42. Okay, so actually F equal 1 may be executed before D equal 42. So F equal 1 and then read 1 and read 0 and then D equal 42 is returned. That's possible. So this program does not properly pass the message. Okay, and then so people add some mechanism to control concurrency. So for example, if you use a release store and then acquire load, then somehow when this acquire reads from this release, there is some synchronization happens, and then you know that you should read 42 because there is some kind of synchronization happened. Okay, and then anyway, point is how we model this phenomena. Okay, that's the question, and then that's open, long-standing open problem. And then people try to find the right model. Okay, so there are two approaches: axiomatic semantics approach and the operational semantics approach, and both has pros and cons. And then it's still open, but very close to the solution. So our community is working hard on this. Okay, and then I will skip relaxed memory, and then I will tell you So this first paper, operational paper by Singh and Lahab, this one extend the notion of linearizability on relaxed memory model. Okay, so previously linearizability was on SC model, and then this paper investigate what happens in the relaxed memory model. And then second, durable linearizability extended to the non-volatile memory. This is by Victor and other people. And so, and there is already notion of durable linearizability for non-volatile memory, weak memory, plus non-volatile. And then they developed proof technique, very modular and nice proof technique for that, proving linearizability. And then finally, this paper developed compositional way of proving linearizability, compositional theory of linearizability. Okay, so is it good? Okay, good. That's all. Thank you.